Dina Ghazi. I got my master's in civil engineering from University of Victoria, where I had the chance to work with Sardar. And then in January 2025, I joined HDR as a hydraulic structures EIT. HDR is a global employee-owned company with expertise across engineering, architecture, environmental, and construction services. In water infrastructure sector as well, HDR has a strong experience with complex dam, reservoir, and hydraulic structures projects. These rankings, industry rankings here also shows HDR a strong presence in hydropower, dams, and water supply. I'll be discussing nonlinear analysis of concrete dams. This is a topic relevant to dam safety and type of work we do in hydraulic structures. I'll give an overview of the main concepts and the important assumptions that need to be considered for nonlinear analysis of concrete dams. As you may know, not all concrete dams behave in the same way. Actually, the dam type controls the load path, therefore, it controls the assumptions we make in the analysis. Gravity dams, the first one in the screen, the top one, mainly relies on their self-weight and foundation resistance to maintain stability. Arch dams behave differently. They transfer a large portion of the reservoir load through arch action to the abutments. And multiple arch or buttress dams can be efficient structurally, but they may also be weaker in certain directions, depending on the layout and reinforcement. Uh, as mentioned, gravity dams rely on their self-weight. So when we analyze a gravity dam, we are asking whether resisting forces, which mainly achieved by weight, friction, cohesion, and foundation shear capacity, are enough to balance the driving forces. For this type of dams, the failure planes may develop through the cracked concrete, weak lift lines, or dam foundation interfaces. So we should be careful about these failure planes. For arch dams, the behavior is more complex actually because the load path is strongly three-dimensional. Part of the load is carried vertically by cantilever action, but a large portion of the load is transferred through arch action to the abutments. That means that abutments are critical. They are not just a structural support, they are part of the system. If the abutment rock is weak, the overall response of the dam can change. Mass concrete dams are built in blocks, vertical blocks actually, and horizontal lift lines. So these surfaces can be potential planes for opening, sliding, or stress redistribution. So in nonlinear analysis, the model should reflect the actual dam foundation contact, lift lines, and contraction joints as much as practical. Before starting the model, we first need to know the purpose of analysis. Collect available input data and select the modeling approach. Actually, a clear plan keeps the model tied to the decision and helps make sure that the analysis is defensible. One of the key inputs is material properties. For concrete dams, dam-specific properties should be used whenever possible because, as you know, uh, concrete properties can vary mm, with different conditions such as age, location, moisture, and testing method. And also for uncertain inputs, sensitivity checks helps confirm the conclusion is reliable. Um, Also, a reliable nonlinear analysis requires a consistent loading sequence from the initial static condition to the governing seismic or extreme load cases. One of the most important assumptions in nonlinear analysis of concrete dams that needs particular attention is uplift pressure. For gravity dams, uplift directly reduces the effective normal stress and it reduces the sliding resistance. A drainage system in dams can reduce this uplift pressure, but we should be careful that the assumed drain location and the crack length influence the pressure profile that we use in stability check. So we should be careful that in nonlinear analysis, this profile should match with the model behavior. Actually, with the model behavior should be matched with reality. I mean. In seismic analysis, the foundation is not just a boundary condition. Its extents need to be large enough so that the model boundaries don't artificially affect the dam response. But at the same time, it increases the computational cost. So the foundation size should be selected based on the required accuracy and the analysis objective. In this picture, you can see the recommended foundation size provided by USBR. During seismic loading, the water adds inertia adds, and it creates a hydrodynamic pressure on the dam, which can influence the overall dynamic response of the dam. The dam reservoir interaction, as you see here, it is modeled by fluid elements, but it can be modeled with different methods depending on the required accuracy and the purpose of the study. A simpler model that can be used and we usually use here is added mass method that can represent the water inertia without explicitly modeling the elements. But be careful that it depends to the purpose of the study and the complexity of the model. Okay, after collecting the main modeling inputs, we need to bring them together into a clear analysis workflow. We typically begin with linear analysis, which helps us identify where stresses or shear or the demands exceed the expected capacity and provide the basis of nonlinear analysis. So we need that. And in general, the goal of the modeling is to have a model that behaves as a coupled system together, not as separated components. A good nonlinear model is not necessarily the most complicated model. It is the model that captures the system behavior in a defensible way. Numerical choices are not just software settings, they affect both the accuracy and the computational efficiency of the analysis. Different finite element tools can be used for meshing and analysis depending on the complexity of the model and the objective of the study. The point here that we should keep in mind is that the quality of the results depends on the engineering assumptions behind the model. The first output we usually review are the mode shapes of the dam, which shows the global deformation and frequencies. They help confirm that the model is capturing the realistic system behavior and gives us a baseline for understanding the nonlinear response. Another output to review is the stress demand plot. These plots guide us see where the highest demands develop during the analysis and which regions may need closer evaluation. Uh, Another point that is good to know is that the analysis results shouldn't be presented only as plots or numerical outputs. We should interpret results in terms of what they mean for a structural behavior and dam safety decision making. This includes identifying the controlling mechanisms and determining whether the response is acceptable for further evaluation. And we need to do interpretation as always, as all others kind of finite element modelings. And before relying on nonlinear results, we should do basic checking and accuracy review. We should review force checks in case of dams, including reactions, base shears, and contact forces. And another check, which is important, is energy balance, especially for explicit analysis of dams. Also, benchmarking is another important checks and comparing the results with handshakes and simpler models or other finite element softwares helps confirm that the model responses are reasonable. Okay, let's look at some project examples at HDR. Here you can see a project. Actually, I wasn't involved in this project as I didn't join with HDR that time. But my manager here, Ali Rasak, was a part of the team for this project. The project this project involves a RCC dam, as you can see here, to replace the existing upper and lower embankment dams. This RCC dams has a 140-foot tall and crest length of approximately 400 feet. Um, it was um, um, it was a potential dam actually. And here you can see the LS Dyna model developed for the dam. Two configurations were considered, a straight or gravity dam and a curved or arch dam, as we talked about. Hydrodynamic loads were estimated using added mass method, and the ground motions were applied at the base of the foundation. The model also included contact definitions between the blocks and between the dam and foundation. The design criteria for this dam focused on both dam safety and water delivery requirements. Um, the key aspects, including displacement, stress demand, cracking, and post seismic stability, were considered for doing this analysis. And here you can see the displacement response of the dam for both configurations, the straight one and the curved one. The model was analyzed using the Chile earthquake record, and as the motion progresses, we can compare how each configuration responses. And as you can see, the curved geometry helps limit the lateral displacement, and the maximum is lower than other configuration, the straight configuration. For a straight dam, the deformed shape at the end of the simulation here shows more localized movement in some blocks. While for curved dam, the deformation is more distributed, which shows the benefits of arch action in transferring loads. And here you can see the contour plots of principal tensile stresses of the dam. Um, for this evaluation, the dynamic tensile capacity was taken as approximately 270 psi. So the gray region here shows the areas that remains below the tensile capacity. For the straight configuration, the maximum tensile demand occurs early in the response. And as you can see here, there are more concentrated stresses at some of the blocks. And another project that I was involved in is Rostam. Rostam is located on Skagit River in Washington State, and this one is the most upstream of the three Skagit dams. Another ones are Diablo and Gorge Dam that we were worked on those two as well. And Rostam was built between 1939 and 1949. Rostam is a variable radius concrete arch dam with height of 540 feet and crest length of 1,300 feet. And the analysis of Rostam evaluated the static and seismic performance of the dam under different reservoir conditions. The challenging part for me was the complex geometry of the dam, because the dam had curved block interfaces, which made the FE meshing and model development more complicated. And my role was do a part of FE meshing, analysis support, and report drafting. And here I should thank to Ali Rasek, my manager here at HDR, which helped me a lot during this project. And key messages here is that the dam type and construction history should drive the model, not software convenience. Linear analysis remain essential for screening, interpretation, and comparison. Nonlinear analysis is most useful when it captures physical mechanisms, including cracking, sliding, joint opening, and load redistribution. At the end of the modeling process, the goal is to have a model that behaves as a coupled system and captures the system behavior in a defensible way. Also, sensitivity studies and verification checks are required before using nonlinear results in dam safety decisions. Thank you for your time and attention. I really appreciate your time, and I would be happy to discuss any questions or comments you may have.
Hey, thank you very much, Dina.
Of course.
That was very timely. It's not too long that bores us, but it was very interesting as well. Is there any question from the students here? Yeah, go
I have
ahead.
a question about the sensitivity analysis. Are you just looking at like best and worst case scenarios, and what are you basing that off of?
Did you hear the question, Dina?
If I understood, let me.
It was
Uh,
about the sensitivity analysis and the purpose.
right. As I mentioned, in case of concrete dams, we need to collect all inputs, but it may in some cases, there might be some inputs that we are not sure about, and we need to do just an estimation. But yeah, as you know, we do sensitivity checks. For sensitivity checks, actually, yeah, we need to consider the maximum and minimum limits. But as you know, we picked the value that after that, when we increase the input, it doesn't affect the conclusion, the result, the output results. So we pick the optimized value.
Thank you.
Did you?
Thank you. Thank you. Yeah, that's also we do in our classes as well. Like I call them upper bound and lower bound just to see how sensitive your results are. Sometimes some inputs may not be so important. For example, in your project Poisson ratio, you can change that and see how sensitive your results are before going and start looking for the exact number of Poisson ratio. Maybe it's not so important. And you say, I did a sensitivity analysis on Poisson ratio, and I realized it was not so important in my results. So that's why I go with like 0.2, for example. Any other questions?
I have a
Sure, go ahead.
So I'm just wondering, in engineering practice, is it mainly about the process before the failure, before the dam failure? Any like a project will analyze the failure process?
Yes. Can you repeat the question? I'm
I
not sure.
couldn't hear clearly.
Oh, maybe you can come here closer to them. Yeah. You can maybe sit here. Yeah.
Hi.
Yeah.
I'm just wondering, in engineering applications, is it like the most of the projects is mainly focused on the dam behavior before it failure?
Actually, it depends. It depends to the purpose of analysis. As I showed you, this project, for example, the design criteria was different. They focused on the dam safety as they were replacing the existing dams. But in another one, let me this one, this is an old dam, and the goal was to see the behavior of the dam on after seismic events, and we needed to evaluate the post-seismic behavior in case of cracking or failures. So to answer your question, it depends. Actually, it depends to the purpose of a study and the required accuracy.
So if it is about the large deformations, so I know one limitations of traditional FEM is that if it comes to the large deformations, the mesh will have the distortions.
Distortion.
Yes,
Yeah.
problems. How you're gonna address the FEM, any method to address when it comes to the large deformation problem?
Um, as if I understood your question, um, just correct me if I'm wrong. You mean that the limitations of the software may affect the large deformations? We cannot capture large deformations.
Yes,
To-
the mesh gonna have
Mhm.
the distortions
So
problem.
basically, how do you manage mesh distortion in your analysis when you turn on large deformations, and if the element is undergo a large deformation that may distort the mesh, how do you make sure that mesh distortion is managed properly in your analysis?
Actually, first, if I answer that from scratch, we use hypermesh software here to do meshing, and it's a strong software to do meshing. So we make sure that we have a nice mesh, and if we get the distortion for that region, we may need to closer evaluation. We may need to do another simpler model for that part to do a closer view of that area and look at that area more closer, maybe. To make sure that the meshing quality doesn't affect the results of the overall response of the dam.
Okay, thank you.
Thank
But
you.
maybe Sardar can
Yeah,
answer
yeah,
that.
no, I think I may just need to add something about meshing. So meshing affects the results quite significantly, and if you don't properly mesh the geometries, what happens is under large deformation, the mesh may distort in a way that the software gives you an error. So you need to have a very clean mesh, meaning the aspect ratio of elements are not too high. For example, if you have elements that they are too long, but the thickness is small, they are more susceptible to kind of mesh distortion during analysis. So you need to make sure your meshes are kind of have similar aspect ratio. And actually, in ANSYS Workbench, there is a metric that tells you how much your elements are like the distribution of your element aspect ratio. So you can see if this is a good mesh or not. And then you can re-mesh and see if the distribution kind of is more uniform.
Yeah, thanks, Sardar, for
Of
explaining that
course.
more clearly. Yeah, as you mentioned before, doing the analysis, we do quality checks of meshing.
Any other questions? Maybe just I can ask something about the boundary condition. So if you go on slide 26,
Yep.
yeah, so what does what like there are different colors here. What do they represent? What's the difference between like blue, red, and if they are different blocks, how do you define the boundary or the contact between these different blocks?
Mhm. Actually, these colors are visually codes. It's not some FE. There isn't some FE concept behind that. It's just the color codes we define for each blocks to shows that these structures are made of different blocks, and as you can see here, for example, between the blue and red one, you can see a line. Actually, that's a surface. That's a plane between these two blocks, and this is the plane, as I mentioned, we call it contraction joints, and it's a potential plane for opening, for sliding, and for stress redistribution. So we define contact, the nonlinear actually contact between these two blocks, and the nonlinear behavior of the dams comes from these interfaces, and that's the most critical part of the dam. And also at the bottom of the dam, it's not clear here, but at the bottom of the dam, each block has a surface. That another interaction that we need to define is that plane. Those planes contact with the bottom foundation. For that surfaces as well, we define nonlinear contact to capture the nonlinear behavior of the dam.
Thank you. So in our course and in simpler project, we usually define like fixed or pinned. They are very idealized condition. In reality, in cases like that, sometimes you need to model friction between different planes or sliding. So you need to define more advanced contacts. And this is one of those scenarios that in this course, obviously, we don't consider. We assume everything is fully bonded to simplify the analysis, but in practice, in scenarios like this, you may end up defining complex contacts, and you may spend, I guess, days on understanding what's the more realistic contact to be defined for that particular analysis. Also, Dina, we have some students here that they model, like their project involves modeling reinforced concrete shear walls. I wonder if you model rebars here, and if you want to do a simple approach in considering rebars, what do you typically do?
No, these types of dams, curved or straight dams, they don't include rebars. Actually, they are mass concrete. We don't have any rebars in this type of dams. The dams, the buttress dam, as I showed you, this one, the bottom one, multiple arch or buttress dam, they call it. It has some reinforcement and layout of reinforcement. But for gravity and arch dams, which are usually and commonly used, we don't have any rebar. We don't just have the mass concrete.
Interesting. Is there someone in your company who has done modeling of like buttress dam who we can reach out to in case we want to model like rebars when they're inside like concrete?
For sure, yeah. Ali Rasek, my manager here, is a good source, and I can share his email. I can ask first him, but I can share his email with you if students have any questions. They can reach out to him.
Awesome. Yeah, we have some students who are using Dina, and it would be very
Interesting.
helpful. Yeah.
Sure.
Thank you.
Yeah, of course.